Mm. So we're looking at the situation where we're pushing on an object, but because we can't get directly behind it, we're pushing on an angle. And we're pushing down as we push the object. This means that we're applying force into the surface. So some of this force is going into the surface. Some of the force is going parallel to the surface. The force that's going into the surface is just going to increase friction and make things harder. So this is not a good, I don't recommend this to start with. Okay, so here's our problem. Eric is pushing a 10.2 kilogram box, which is being represented by this chemistry textbook, with a force of 100 newtons directed 30 degrees down from the horizontal. So component of it into the horizontal, component of it parallel with the horizontal surface. Coefficient of friction is 0.1. And if you remember, to find the force of friction, we multiply the coefficient of friction by the normal force, which is perpendicular to the surface. What's the acceleration of the box? So this comes down to one of these F-net problems. So we're going to pretend that I'm pushing it this way, or Everett's pushing it this way. I'm going to define this as positive x. I'm going to define that as positive y. Now, I've done all these calculations, but I think you'll agree that they're not that hard to do. A 10.2 kilogram box has a force of gravity of 100 newtons, 10.2 times 9.8. Handy? I think so. Okay, 100 newtons directed down from the horizontal. 50 newtons, or 100 sine 30, is going to be going into the surface, and 87 newtons is going to be going parallel to the surface. All right. Now, I think these are handy. Break it up into an XY table. So some of these components act in the X direction, in other words, that way. Some of them act in the Y direction, and the ones that act in the Y direction are going to have an impact on friction. And that friction is then going to have an impact in the X direction. So I think a table is kind of a handy way of keeping track of all this information. All right. Let's start out with our applied force. So we've done our SOHCAHTOA thing. In the X direction, there is positive 87 newtons. Good. At least some of this force is going into doing some good. 50 newtons is going down into the surface. It's going down, so we say it's negative 50. Force of gravity, 0 in the X direction because the surface is parallel with the horizon. Okay. And we're standing on the Earth, so that's all good too. However, the force of gravity is negative 100 newtons down. Now, an important thing to realize is that vertically, since that book is not accelerating, the net force in the Y direction has to be 0 newtons. There is no friction in the Y direction. That's 0 newtons. That means that negative 50, negative 100, all have to be balanced off by the normal force, which is going to be positive 150 newtons. Okay. The normal force does not act in the X direction. Force of friction is mu times the normal force. Mu is conveniently 0.1, and so the force of friction is negative 15 newtons. Friction always acts opposite the direction of motion. So the net force in this case is going to be 62 newtons, and that is going to be to the right. To find the acceleration of the box, we would just divide 62 by the mass, and we'll get something like 6 meters per second squared. And that's the whole pushing on an angle problem.